Assalamu alaikum wa rahmatullahi wa barakatuh. Good evening. This presentation will talk about approximation algorithm. We will explain vertex cover problem which can be solved by using approximation algorithm. Next slide, it will be the outline about what is optimization problem and how to deal with NP-hard problem and approximation algorithm to solving problem and how solve the vertex cover problem using approximation algorithm. Also, we will talk about proof for performance guarantee of this algorithm. In the next slide, we will see in mathematics and computer science an optimization problem is problem to find best solution for all feasibility. Best solution for all feasibility. Feasible solution. The objective may be either minimum or maximum, depend on the problem considered. I will explain what does mean by minimum and maximum just a few minutes. A large number of optimization problems which are required to solve particular NP hard. It is not possible to design algorithm that can find exactly optimal solution to all instances of the problem in polynomial time in this size of input. Approximation algorithm used to solve many optimization problems. Optimization problem is used to find best solution from all visibility solution. Also, we have large number of optimization problem having exponential time complexity like NP hard. It's like TSP problem, travel salesman problem, and zero knapsack problem and vertex cover problem. It is impossible to design algorithm to find exact optimal solution. NP-hard problem in this stand of problem for polynomial time. So it's important to understand how we deal with NP-hard problem. The optimization problem can be either. We also talk about either minimum or maximum. In TSP problem, we try to minimization problem because we want to minimize the cost. But in knapsack 01 knapsack, this problem is need to maximize because we want to maximize profits. Next slide, we have three algorithms when we want to deal with NP-hard problem. Brute force algorithm, heuristic algorithm, approximation algorithm. With NP, it means non-deterministic binomial. We have P, it's easy problem called binomial, and we have NP, it's non-deterministic binomial, and we have NP complete, it's more difficult from other two type, and also we have NP hard, it's very difficult kind of problem. In the next slide, brute force code enumeration strategy, it's give guarantee to find optimal solution but no guarantee in running time. In heuristic, in intuit algorithm guarantee to run binomial time, we have guarantee to run in binomial time, and no guarantee with the quality of solution. It means some of problem we will get solution, and other problem maybe will not get any solution. Approximation algorithm, its third type, it's running in binomial time. It's running in binomial time, and guarantee to get solution which is close to the optimal solution. The challenge here, we need to prove solution value in this close to optimal value without even knowing what is the optimal value. In the next slide, we will make definition about approximation algorithm given by optimization problem B, and algorithm A is said to be approximation algorithm for P. For given any instant I, it will return an approximation solution. This is a feasibility solution where P is an optimization problem and A is approximation algorithm. We have P, optimization problem, and A, approximation algorithm. I is instant example for P. A star, optimal value for instant A, and A for I, value for instant I, generated by algorithm A, approximation algorithm. So A star for I, optimization value, and A for I, value of instant that generate. So we have two types of approximation algorithm: absolute approximation and relative approximation. Absolute approximation, absolute approximation algorithm, and there exists constant k, such as for every constant, every instant I of p, a star for a minus a star for I, bounded module less than or equal k. For example, planar graph coloring. I will not talk about this type of approximation. This type I will talk about him in this presentation. Relative approximation. A is an relative approximation algorithm if there exists constant k, such as for every instance I of p max a star for I divided by a star for a comma a for I divided by a star for a, it will be less than or equal to k. This is talk about vertex convert. The next slide we will see indirect graph G. It's contain B and E. B it refers to vertex. E it refers to edge. Also on visibility solution we have subset C. It's bound, it's under or at related V, such as the less one vertex of every edge of G belong to C. So C is belong to V, and at least one vertex of every edge of G belong to C. The value solution in this size of cover bound module C, the goal is to minimize it. Next slide, we will see this example about is this graph vertex cover or not. We will take this C as a solution, one for 1, 4, and 7. 1, 4, 7. We will remove each edit that related with 1 and that related with 4 and each edit that related with 7. So each edit related with 1 will remove this edit 1, 4 and this edit 1, 5 and this edit 1, 2. Also we are going to 4 and delete each edit that related or selected each edit 4, 3, 4, 7, 4, 5. And also we go to the last element in this group C. We will delete 7, 7, 6, and 7, 5. So we have two edits. We can't delete them because so it is not vertex cover. In the next example, we will see example 2. Same paragraph, we will select different vertices like 1, 2, 3, 5, 7. In 1, we will delete 1, 4 and 1, 5 and 1, 2. In 2, we will delete 2 ones, also delete last previous step. We will delete 2, 5. After that, we're going to the element 3 vertex 3. We'll delete 3, 6 and 3, 4. Also going to the element 5 and delete 5, 7 and 5, 4 and 5, 1 and 5, 2 to also deleted by previous step. Also we're going to the last element 7. We'll delete 7, 6, 7, 4, 7, 8. So we will in this paragraph no edits are remaining. So this edit all will selected will cover. So it is a vertex cover. Number of elements in this module C equal to 5. The next slide, we will see this also example. This is less than from this example. This is bound for 5. We will see this is maybe bound C for 4 only. So we'll select 1, 4, 5, 6. Also we'll delete each that related with any one of this vertex. We'll delete 1, 4 and 1, 5 and 1, 2. Also we'll delete for element 4, 4, 3, 4, 7, 4, 5, 4, 1 also. And then going to the element 5, vertex 5, we'll delete 5, 2, 5, 1, 5, 4, 5, 7. Also we'll delete going to the element 6 and delete 6. So we will delete this graph will cover all vertices. So it is a vertex cover. The next slide, we will see this example A. This is graph without selecting any edge. In the B and C, in the B, we will select, this is a triangle vertex because we are select all edge. This is not minimal. It's this is maximum. So in the C and D, we will select just four edge to solve this problem, and it will be vertex cover. In the next slide, we will talk about time complexity for brute force cost. It's for n element 2 power n, so it is exponential big O 2 power of n. It is exponential complexity. In the approximation algorithm, so we see the brute force cost time complexity. Now we talk about vertex cover approximation algorithm. So we'll start with C. C, its group of solution. It's start with 0. Start with 0. We'll analyze this group. See the solution. See it as null. Then we pick an edge. In the next step, we will pick an edge UV for the seat of edge E. It's from seat of edge E. Then added vertex of this edge to our solution by writing C equal to C, its union to U and V. After selecting U and V, we will remove all edge indicate on either U or V from E. Anything indicate to U or V from E will delete. After that, we'll repeat all this procedure, all this step process till edge NE are removed. After that, we'll stop and return the result in C. This is also vertex cover approximation algorithm formal. This is the right part episode code where C equal to null and E equal to G and E. It's edge and vertex while E is not empty, is not null. Let's select U and V and arbitrate edge for E. We will select any edge, arbitrary edge, anyone we can select, and then add this element we are select to this U and V we are select to our solution. After that, we'll remove from E bar every edge indicate to U or V. We will repeat this procedure. We'll repeat this until E equal to 0, equal to null. After that, we'll return our solution. So big O for this vertex V will take N, not more than, and E, it will take time N power 2 because N edge and E edge and V is a vertex, so it's big O, it's big O N power 2. It is polynomial complexity. This is about time complexity. In the next slide, we will take this example to execute, to actions, what happened. So in this, we will see C of solution, it's empty. And E, this is all edge in this graph. While E not 0, this is 0, this is not null. So we will take any edge, we will select 1, 2, suppose, and we will remove each edge that relate with 1 and 2. 1, 2 will remove, 1, 4 remove, 1, 5 remove, 2, 5 remove, and we'll add them to the C. And not add them to the C, it will remove them, and then after that we will select other vertex until E bar will be null. So next slide will explain. By selecting 1, 2, we will delete 1, 2, 1, 4, 1, 5, 2, 5. After that, we will select by C equal to null. This is first step. E edge, all edge in this graph. While E not, this is not null, this is not. We will select 1, 2. Edge U on V. After that, we'll add this 1, 2 UV to our solution. 1, 2. This is in this step 5. After that, we'll remove any edge indicate either U and V. Either 1 and 2 will remove. After that, we'll return until this will be null, and then we'll get our solution. So we are select 1, 2. After that, we will select 5 and 7. So we will delete 5, 4, 7, 4, 7, 6, 5, 4, 5, 1 was removed, 5, 2 also it was removed. After that, we in the next step we will select other element, 3, 6. In the 3, 6 we will remove all edits. So in this step we will see E bar. This is will be null. So we will stop and get our solution C. So in this graph we will see we have two type of while proven from us in this algorithm. We will use term called maximal matching and matching. What does mean by matching and maximal matching? Matching indicate edge seat in the graph. Seat of edge. This is edge without comma vertex. There is no vertex comma. 1 and 4 and 1 and 5. This is comma edit, so this is not matching. But 1 2 is matching, 3 6 is matching, 5 7 is matching, and a matching became maximal matching if is no more edge can be added to it. No more edge matching. This is only 1 2 5 7 3 6. We can't add any edge with it, should be without comma vertex. So this is a maximal matching. So C, this is our solution 1 2 3 that will getting by approximation algorithm, and matching it will be 1 2 3 6 5 7. So module C equal to 6 1 2 3 4 5 6, and module M it will be equal to 3. So module C it equal to 2 multiplied by module M. Module M maximum matching, maximal matching, and C it's our solution that we are getting by approximation algorithm. Vertex cover performance proof. The edge picked by algorithm is a maximal matching, so we'll reverse it by M. Hence, C is vertex cover. C vertex cover. The algorithm running by polynomial of input size. The optimization vertex cover. C. This is optimization vertex cover. It must be cover every edge in M. C. Optimization vertex cover. It should cover every edge in M in maximal matching. Hence, C star contain at least one edge of endpoint of each in M. So we will see module C equal to 2 multiplied by module M less than or equal to multiplied by module C star. Thus is two-factor approximation algorithm Vertex. We will complete next slide. We will see bounded C is equal to 2 multiplied by M less than or equal to. This is our formula that we will get in the previous slide. C is less than or equal to 2 star C star, and 2 C star is greater than or equal to 2 module M. So 2 module C star is less than or equal. Just we are replaced 2M. This is 2M by C. Sit here. After that, and this will be same 2 module C star. It's greater than or equal to bounded C. Module C it's less than or equal to module C star. On the next slide, we will get this assignment. Apply approximation algorithm on the above graph. This is a graph A, B, C, D, E, F, G, we are, and then find vertex cover seed and the number of vertex in that seed. Question 2, find the minimization vertex cover as in this problem. Verify C less than or equal to multiplied by bounded C star. Also, this is next part. We will talk about liner graph coloring, and this is reference. And thank you for watching and listening to this video.